So we've seen that in order to approximate the area under a curve, we can use a bunch of little rectangles of equal size, and then add up all the areas of the little rectangles. Well, the more little rectangles we have, the closer our area is going to be to the actual area underneath the curve. So ideally, we want to have, you know, lots and lots and lots of little rectangles. So if we can find a mathematical way to add up the area of, say, 100 or 1,000 little rectangles more quickly than actually calculating the area of each one individually and then adding each one up, then that's going to make our approximating process much smoother. And so the notation and kind of mathematical concept we're going to use is this summation notation, where we're taking the sum of a certain function at a bunch of tiny little values. So this is also called sigma notation, and this is the big symbol. This means that you're adding a bunch of stuff up. This is a sum. And the summation notation, so this is my ith term. Okay, so I've got a bunch of terms here. And if I want to add up a bunch of terms, my I starts at 1, so I take the first term, and then I add it up to the second, add the third term, the fourth, all the way up to the nth term. Okay, so n is the last term that we end up adding. So this is just what the general formula looks like, but we actually have all these special summation formulas. Okay, so there's just a ton of these things. Most of the problems that we're going to do are going to deal with these first three. Okay, and I might even throw in one that uses this guy. But basically, if I'm taking the sum from the first term up to the nth term of just I, which kind of replaces the a sub I can rewrite it as this. I can just take the n, multiply it by n plus 1, so 1 bigger than n, and divide it by 2. Okay, and there's different formulas depending on what you're doing. So this is pretty conceptual at this point, so let's actually apply this and see what happens. So first I'm going to look at how we can write things into sigma notation. Okay, so if I've got this sum, I'm adding these things up as they go. The thing that's changing in here is this term. Okay. Now in our sigma notation, our i's and our n's always are whole numbers. They're numbers that go from 0 or 1 up to the highest, but they're always whole numbers. So in this one, the thing that's changing is this number. So that's my I. That's the number I'm plugging in. Okay, so I could write this as, take the sum of this expression. Okay, I. And our i's are starting at 1 and they're going up to 4. Okay, so these two things represent the same thing. Okay, a simpler example would be, let's say I want the sum as I goes from 1 to 10 of, I don't know, 3i plus 2. Okay, well that means I'd be taking 3 times 1 plus 2 plus 3 times 2 plus 2 plus 3 times 3 plus 2 plus 3 times 4 plus 2. Okay, all the way up until I've got 3 times 10 plus 2. Okay, now we could just go through, since we have a small number like 10, we could find each of these. Okay, so it'd be 6 plus 2 is 8, 4 plus 2, okay, 6, and then we'd have 9 times 2, which is 11, we keep going up, up, and up, up, and then we can add all those little things together and get the overall sum. But we want an easier way, because what happens if I want 1,000 of these? I don't want to have to calculate 1,000 little values and then add them all up. So that's where our summation formulas come in. So we can use this okay, with our summation formulas to make calculating what the first 10 i's added together would be. Okay, so if you look at our summation formulas, we've only got them for I squared, I cubed, I fourth, I fifth. Okay, so we need to have terms that just have these. So what I want to do is I want to distribute my I here. So I'm going to have, this is really the sum as I goes from 1 to 10 of I cubed plus I. Now, a lot of the same rules that we've had for derivatives and antiderivatives and limits apply to summation notation as well. So you can treat this kind of the same way as we treated derivatives and all that stuff, okay? So I've got a sum here, which means I can give each term its own sum. So this is the sum as I goes from 1 to 10 of the first term here, plus the sum as I goes from 1 to 10 of the second term. Okay, and our constant rule applies also, so if I had, let's say there was a 2 here, I can pull that out in front and do the 2 here. Okay, so we're going to be able to isolate these I terms, okay, by multiplying things out and getting the I alone. Well, my I cubed, okay, if I'm taking the sum of an I cubed, I can just turn it into this. Okay, so it gets rid of the sum and just gives me a straight algebraic expression. Okay, so n squared, n plus 1 squared over 4. So that's what this turns into. This is n squared, n plus 1 squared over 4. This is just I, okay? That's n plus 1 over 2. Okay, and n, remember this is our n. It's going up to 10, so that means I just have to plug 10 in for all these n's. So I have 10 squared is 100, times 11 squared, just 121, over 4, plus 10 times 11 over 2. So if I divide by 4, I can get 25 times 121. Which is going to give me nope, that's not right. 3025. This one is going to be 110 divided by 2, which is 55. Okay, so that's what the sum of the first 10 terms would be. Okay, so that's the real basics of sigma notation, and we'll get more practice in, and we'll actually apply this in the next lesson to our area under the curve, which is kind of what we're building up to, and we're working closer and closer and closer to doing the integrals, which involve the antiderivatives. We're just trying to relate those so that we know what it really means and what's really happening when we take an integral.